Then everything is in Gemixer VM. So let's get into it, and roughly before we dive in, I'll explain. There's in the Graypaper, there's Appendix A and Appendix B. Appendix A later came to be called the internal PVM. This PVM knows nothing about structures whatsoever. It doesn't know anything about the rest of the gem. It doesn't know about assurances, work packages, or work report. Nothing. It knows bytecode in, result out. This is used. This is why it's separate repo as well. It's a complete universe onto its own. This is used by some functions in the Gemixer project that's called to it by passing arguments. This is Appendix B. This is the external one. This is the part that is aware of the rest of the world. We are now going to discuss from the ground up on the internal one. Start from the bytecode with the definition of the functions, and we'll see where we progress. Okay. Let's dive in. I'll share my screen. Everybody can see? Yeah. Okay. Let's sync here with the basic definition. Okay. We start here. The internal PVM is defined as a simple function. It's a binary, counter, gas, registers, and memory. And the return is exit reason, updated counter, updated gas, updated registers, and memory. That's all. Where can we see that? Here. Psi, the PVM function, takes in binary, Y. This is what? Counter, gas, registers, and memory.
What does this counter count?
The counter does not count. The counter is the index into the instruction list, so to say, array. So you start from position A, there's an instruction there. Let's say the instruction occupies 3 bytes, so the next instruction will be at the position 4, right? 0, 1, 2. No, will be the position 3.
Okay. So basically the counter says, where do you PVM start reading the code? So there's a big chunk of code and there are a lot of instructions, and you say, start here, like the entry point.
Start here, and there you are there, and next one you are there, and next one you are there, and maybe there's a jump instruction, we will get to there, so you're moving back to another place, right? It's your index into which instruction is next.
Okay. So like in the Turing machine, there's a strip with a lot of symbols. Let's say start in the symbol number 11. You can start on any symbol, right?
Yes, you can start on any symbol. Practically, we don't do that, but yes, you can. Okay. Registers. Registers are a list of 13 64-bit integers. Nothing more, nothing less. Just a list of 13 numbers. Memory.
And memory is this similar to the actual CPU, hardware CPU, where you have some places where you can put some data that you can use to process, right?
Yes, I imagine it mimics the hardware configuration. That's one of the claims, that PVM is better than Ethereum virtual machine, because Ethereum virtual machine is stack based, while actual hardware is register based. So when you write binary to run on the PVM, which is registry machine, this binary is easier to convert, possibly faster to convert, to run on native, because native is register machine.
Yeah, and it's compatible with the RISC-V architecture, right? So probably RISC-V has 13 registers. That's why the PVM has 13 registers.
Yes. Now memory has access pattern, like it's accessible by page, but let's not dive into that right now. We can imagine memory to be a simple list of bytes. So a list of numbers 0 to 55, the list has a length of 2
We're
to the power
we're
of
not seeing
32.
your screen now. It's
You're not?
no. Yeah, now we are. Yeah. Okay.
So this is not completely true to the implementation because there are details, but it's not important right now. We can think of it as simply a list of numbers, each 0 to 255, and the list has a length or maximum length of 2 to the power of 32. So this is the world state we have, right? We have a counter where which instructions we're going to run next. We have gas, we have registers and memory. From now on, it's about each instructions. How does it manipulate those registers and memory? So how do you feed arguments into the PVM? How do you start? We feed a binary that is defined like this. It's better seen here. This. So it encodes.
Can you increase a little bit the font size?
Sure.
Of the Graypaper. Maybe if you take out the menu, whatever. Yeah. Okay.
Better?
Yeah.
Okay. Thank you. This is the binary, the Y, that we feed into the PVM. It's constructed out of 3 elements. The most important of them are C. C is the list of instructions. We have it a little bit more explained here. Yeah, C, the instruction data. Sequence of instructions that the PVM should perform. These are mostly instructions such as load the number into register 9, read and bytes from the memory, start from address B, load it into register 3, for example, yeah? Add the value in register 9 to the value in register 3, write the result into register 2. These kind of instructions. Next, we have the bit mask. The bit mask matches the length of the instruction list. And the point of the bit mask is to say which indices are the start of an instruction. Does that make sense or not?
Yeah, can you explain a little bit further? So basically,
right, so
for example, if I have 10 bytes, probably the first byte is instruction, and the next 2 bytes are arguments for that instruction. So basically, it will be 1, 0, 0, and then you have another instruction, something like this.
Yeah, let's look at this example program, for example. Okay. We have the instruction, which of course in reality is a number, but for simplicity, load 710, load 85, reduce 71, jump greater than 786. So the bit mask.
So just one question. The load 7 is a different byte, or load 7 is just one instruction, just to understand?
You are correct.
Okay, so the same goes. Yeah, okay. Nice.
Reduce.
Better?
Same thing for reduce, no?
Same thing for reduce, correct. Reduce. So the bit mask says, this is an instruction, these are not an instruction, not instruction, instruction, not instruction, not instruction, instruction, not, yes, not.
Perfect.
Yeah. How is it used? Wait, terrible. Looking at the bit mask, we can learn 2 things immediately. We can learn, one, that our program has 14 bytes because the length of it is 14. Second, we can learn that we have instructions rather than arguments in the indices 0, 4, 7, 8, and 13. Next, we have the jump table. The jump table, I wouldn't say it's not important, but in codes that I have written for test, I've hardly used it. But the jump table is a list of predefined indices where you can jump.
The jump table is part of the arguments, for the PVM? Where is it?
Yes. Yes, there it is. So the binary that the PVM receives is P. P is made from encoding of the length of the jump table,
Okay.
encoding of Z. Z is how many bytes are used to encode the jump table, each byte. Then we have encoding of C, the list of instructions. Sorry, the length of C, C itself, and K. So when we get this binary and decode it, we learn. We essentially what we want to.
Basically, you decode the binary and then you get C, K, and J.
Right, instruction list, bit mask, and
jump table. Okay.
Yeah.
Got it.
Jump table is a way to kind of predefine places you want to jump to. Let's say you want to jump to an index 4. Instead of specifying it via arguments to the jump instruction, you can keep it in the jump table, then just jump to jump table at position N. When I say jump, do you know what I mean? Should I go into that?
Jump means go to line, program line, whatever.
Go to.
Yep, it's a go-to. Otherwise, the program will proceed linearly, one instruction at a time. This instruction, then this instruction, then this instruction. If you want to go back, if you want to make a loop, then you have a jump. So a jump table is a way to say, let's say I want to jump to index 6. Instead of supplying it through immediate arguments to the instructions, i.e. in the program code itself here, you can keep it into jump table and then jump as so. I want to jump to position, jump table at position 1.
Okay.
How are we up until now?
Perfect.
Great.
Perfect. So let's look at single step transition. Is it? Yeah. Single step transition. How does this relate to the PVM definition? If you see here, the PVM, what it does is run single state transition. The exit reason, the counter, gas, registers, and memory are all updated by a single state transition. And then we're looking at the exit reason. If it's play, i.e. continue, we execute again. We call ourselves recursively to Psi. Otherwise, we exit with out of gas, or exit like this, or exit like this. But the workhorse, the one that perform instruction one after another, is a single step transition. Right here. Now, all there is to say much about the single step transition really is that it gets the entities that we've decoded from the larger blob of binary, right? It gets the program, the bit mask, and the jump table. Again, we have counter, gas, memory, and registers, and it performs one single operation at a time. The exit reason is always continue, i.e. run to the next operation. The counter is always updated to point at the next instruction. So let's look at this program, for example. Short program. We'll get to what it does. We start here because K here is 1. We execute a single step, and unless there's an error of out of gas or some failure or another, the machine will progress to the next instruction, which is here, unless something else. So that's what it says here. Unless something else, unless an instruction specifies otherwise, we continue to the next instruction. We reduce the cost of the gas of the current instruction, and we don't change the registers, and we don't change the memory, unless the instruction specifies.
Okay.
How are we?
Yes.
Good.
Now, really, this is all there is to it. From now on, it's jumping into the table of instructions and writing them out in code and performing them out by one. And that's it. So let's look at how a very simple program can be constructed. Let's build the most basic program that loads two numbers into registers. A lot of work I need to do here on spelling mistakes. Loads two numbers into registers, sum them, write the result into memory. That's all. That's all we want to do. In order to load the number into register,
one question: when it ends, it returns the value of the all the registers, right? So someone calling from outside can read this information later, right? For example,
there's a few layers until we get to the outside.
Okay.
Like to be less vague about it.
I'm thinking about the PVM function as a black box.
Yes.
And if it returns the updated register, memory, or whatever, so you can
let's look at the definition. Okay, we ran a single step, right? If the exit reason was continue, we run again. If the exit reason, if we ran out of gas, this is gas. If the gas is below 0, we return the latest counter, the latest gas, the latest register, the latest memory with out of gas error. If the exit reason is internally, we call this panic or halt, like lightning and stop, panic or halt, then we return the exit reason, we reset the counter to 0, and again, the latest gas, the latest register, the latest memory. Otherwise mean other exit reasons. For example, there's a host call exit reason or page fault, memory read exit reasons. Otherwise, the same story. Return the exit reason, latest counter, gas, registers, memory. So there's no. So to your question, yes. The answer is yes. The return value from the PVM is the latest state of the machine, which is the latest register, the latest memory.
The latest state. So basically, if you sum some things on register, whatever, you can read this later and have this this processing value from outside.
Yes, I just want to clarify that the state of the PVM, this internal PVM, is not really exposed to the gem.
Okay.
In our repo, in Gemixer, this is not really exposed. It is being called through two functions. So what the
refine and accumulate. Yeah.
No, even below this. So the refine calls something we call argument invocation. The argument invocation calls host call invocation. The host call calls the PVM, the basic PVM, which we just discussed, which internally does a single step.
Okay. Okay.
So we have some way to go.
We can move there later then.
Okay.
But it's good to know that the PVM itself is not exposed as it is to gem.
No. Now, from now on, I'll proceed to construct this very basic program. If you got the point and you're bored and you want to move on, let me know. I don't have the WebMD document does not cover beyond this point, but I'll do it without. So let me know if you got the point and you want to continue. Okay. So as we said, we want to experiment with the very, very basic stuff. We want to load two numbers into the registry. We want to sum them, and we want to write the result into memory. Okay. How do we load something into the register? We have this opcode 51, load immediate. Let's look at it in the Graypaper. 51. There we are. Load immediate. In general, the name load means that it goes into the registry. The name store means it goes into the memory. So load immediate, take an immediate value, i.e. a value that lies within the instruction code itself, and load it to a register. So we have WA tag, which means posterior value of register A will be equal to VX with no gas cost. Yeah, the gas model is not done yet. All the operations are without gas cost. So
Where is A defined?
sorry?
Where is A come from? What
Yeah,
does it come from?
right here. So WA is W at position RA. W is the registry. Register 1, 2, 3, 4, 5. So WA means W or the register at location RA. The tag means the posterior value.
Okay, and array is the mean. I got it.
Right. This says, look at the byte one after the instructions itself. Look at the value of it. Mod 16, min 12. So let's assume that we want to put
13 because there are 13 registers. So basically,
Correct.
you can't put a value bigger than 12.
The value
Why
can be
more?
definitely bigger than 12, but you cannot
The value
assign it
can,
to a
yeah, but
registry.
the RA, which is the register that you are referring to, can be from 0 to 12.
Correct.
Okay, but
So let's say,
why,
for example,
why
we want
mod 16 and not mod 12?
mod 16, if you look at it in hex, it will take the lower
Because it's X.
4
Okay,
bits.
got it. Yeah,
Yeah,
it's
it
X.
takes the lower 4 bits of the hex. So it's
Okay.
it will be I don't know why it's mod 16 actually.
Yeah, probably
is-
because it's more efficient.
It becomes it's being used later to specify 2 registers in with 1 byte. So you take the let's say you have where can I type freely or draw? Is there a place like this in Google Meet? Like a board?
I don't think so.
Excalidraw, maybe.
Let's see, just a moment. I will check in the activities.
Yeah, there's
Miro.
Miro.
Yeah.
Can use Miro. Yeah, I don't know if you have an account on Miro, but
Miro?
yeah.
Let's see.
Probably it's gonna take some time, but I don't know.
Yeah, I guess not worth to do it right now.
Try Excalidraw. I think it's good.
We will get to it. There is an instruction that uses it, but okay, I'll type it here, or I'll open it just right. Yeah, that's okay. For example, let's say it is used to specify 2 registers in the same time. So if you want to make an operation that sums, we will get to it, the registers 7 and 8, the bytes that specify it will be 0x for x, 7, 8. So the mod 16 will be this one, the 8. The div 16 will be this one. So this allows to easily specify 2 registers with a single byte. This is a useful side effect of the mod 16, but I don't think this is the reason why here is mod 16 to begin with. Truth is, I don't know.
Okay.
All right. So let's say we want to put the value 10 into register 7. So we want to specify register 7, RA 7, and the value here, 10. The instruction starts at 51 because that's the opcode for load immediate, 51. Okay. Next byte is 7. Why? Because we said RA, look into the next byte, mod 16, min 12, 7 that RA, so we will be handling register 7. Now the value. Let's look at LX. LX here is max between 0 and L minus 1, and then min that by 4.
Where is L? Where
L is the skip distance. The skip distance is, we have here, The skip distance is the amount, you can think about it as the amount of zeros for the next operation. Like the skip distance from here will be 2.
Okay.
Skip distance here also 2. 2 and 3. That's the skip distance. So L is the skip. So this LX quantity, you can read into it and try to understand what it says, but I'll spare you the time. What it means really, it's all the bytes until the next instructions. So it means just read all of these, all the bytes until next instruction. So read 7 and 10, read 8 and 5, read 7 and 1. So this is LX, and then the VX, the value which will be assigned into the register, will be read from position of the instruction +2 plus LX, like the number of bytes you have until the next instruction, decode it as an integer, and sign extend it into 64 bits. We are not going to get into the sign extend. There's all sorts of utilities that lie around to manipulate numbers. In our case, it's very simple. 10 is a single byte, so we just put 10. That's all.
Yeah, but if it was a big number, you would, because it's 64 bits, and we have just every byte is just like 8 bits. You need a lot of bytes if you want to represent big numbers. So that's why you have all this like bit manipulation stuff to deal with this. Now I got it.
Yeah, exactly. What if okay, simple example 10, yeah, but as you said, what about if you wanna a larger number than 255, right? So because of the mean 4 here, that means if you put 5, if you manipulate the bit masks such that you will get a 5 here, it will not work. It will be 4. So the maximum bytes we can use for this immediate value is 4 bytes. So let's say if you had an instruction that looks like this, 51, 7, 1, 20, all these hexes, what will happen
Because
is
it's 32, right?
Yeah. So WA or W7 in this case will be assigned this value. This is the sign extension. This is the little Indian representation of the number here. So we have 1, the smallest bit, then 20, then I really need to edit it. Or basically 0, 0, A, right? 0, 0, A, 20, and 1. So yeah, you can assign with an immediate value, you can assign numbers up to 32 bits. How are we so far?
Fine.
It's 32. I've heard that it was upgraded to 64 bits. Is there something?
The registers are 64 bits, and there are some instructions that, of course, operate with 64 bits. But this instruction that I chose for the demonstration is load immediate.
Okay. The load immediate has
bits.
just 4 bits, but there are other instructions that you can like load U64.
Let's have a look. There you go. Load U64.
Got it. So this one has 64 bits.
So load U64.
Basically, on the instructions, you know the size of the data that you are using, right?
No, some of them will be automatically, so to speak, determined by the bit masks. So you know how many bytes are until the next instruction, so you read them all. That's a load immediate one, right? Load immediate gives you freedom to use 1, 2, 3, 4 bytes without having to specify.
Up to 4.
Up to 4. In this case, we could have used load U8, right? We didn't need to use load immediate. Load U8 would have been just fine. As you can see, load U64 reads VX plus 8 bytes. Notice the difference. Load immediate assigns VX directly to WA, to the register, right? So you read a value and you assign this thing into the register immediately. The other ones use VX as an index into the memory. Sorry, not an index into the memory, as a starting position. No, I'm not wrong. Yeah, index into the memory. So this one, that's why this one is a load immediate. You load from the instructions, from the instruction code itself. In the other ones, you use this immediate value as an address into the memory, and then you read 1, 2, 3, 4, up to 8 bytes from the memory, and you load those into the register.
Ah, I got it. So you can't do it more than 32 bits immediately. You have to access the memory. So it should be slower, technically speaking.
Yeah. Okay, the next one is
please.
Yes.
What's the cycling symbol?
Modulo. It means that if the address goes beyond the edge of the memory, it just goes back to 0.
Okay, fine. Thanks.
You have a fixed length memory. If you try to read beyond it, you're not reading somebody else's program. You just circle it back again.
Yeah.
I think we can skip the next one. Both of you are smart guys. There's no need to explain load immediate once again. We said we want to load 2 numbers and add them together. Okay.
Mm-hmm.
That's the instruction for add 32. What was it? 190. Since Wasim has been granted access to the Jamixir repo, I imagine there is no problem to show him Elixir code for the PVM as well, right?
Yeah, let's keep without showing the code for now, just because this is more generic workshop. Let's try to keep it for the last part, showing the actual code, so we can share this content with other people.
Sure. Okay, so we wanted to add 2 numbers. So there's the instruction bytecode 190, and we have WD equals extend to 8 bits of WA plus WD mod 232, right? So W, I remind you, this is the registry. So we add registry A with registry B. We modulo the result because this is add 32. We extend this to 8 bytes, so 64 bits, and we assign the value into the 3rd registry.
Why x4 extend x4 means add another 4 bits, right?
Those x's, they always extend to 64 bits. The 4 means the incoming value is how many bits, basically.
Okay.
Yeah, I can show you the definition.
Okay, got it.
I'm not sure if it's really helpful to. Maybe for you can reason about it easily. I could not.
Yeah, I got it.
So this is X, right? It receives an N 0, 1, 2, 3, 4, or 8, and it converts a number of this amount of bits into an R. R, I'm not exactly sure what it is. I couldn't find the definition of it, but it's widely understood that this means sign extend to 64 bits. What is it to sign extend? It means that if the largest bit is F, I think, like, let's say we have a value like this, 0, A, 1, 0, A, 0, 0, 0. Okay, to sign extend this to 64 bits would be 1, 2, 3, 4, 1, 2, 3, 4, 0, A, 1, 0, 1, 2, 3, 4. So we pad it with zeros. On the other hand, if this was F here, then this would be F, 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 F. This is what the function here is responsible for. It's responsible for extending numbers to 64 bits to put them into a registries at 64 bits.
Okay.
All right.
Okay.
So we were in 192 adds. So we take 2 registries, we module the value, we extend it to 64 bits, and put the thing into the 3rd registry, which of course could be one of those. There's no restriction. All right, there we are. Add. So RA, RB, the indices of the two integers, the registers that we are adding together, they are both specified using the same first byte. RA is the mod 16, and RB is floor division of 16. So if we want to add 7 and 8, this is how we do it with a single byte. 7 is RA, 8 is RB. Now we want to save it into register number 1, so that's RD. So that's the next byte. So far the instruction is 190 for add 32, 87 hex for adding those two. Of course, the order doesn't matter because it's adding, and save the result into register 1.
Ah, now I understand. So basically, when you have instructions that deal with more than one register, instead of like putting the number of the register on different bytes, you use the same bytes to extract both numbers. So you can now I understand.
I think it's just a small optimization for compactness. Like you
Yeah,
could
yeah,
specify yours for yourself. In your own Daniel PVM, you could use 2 bytes for it. It's absolutely no problem. But then again,
Yeah.
why? Right? Because you have only 13 registries, so you will never need any number above 13. So you can use the same byte twice.
Yeah, got it.
Right?
Interesting.
Like every 4 bits allows what? How many? They allow 16, right?
Yeah, actually
0 to 15, right?
Yeah, yeah. You have 4 bits.
Yeah. So yeah, you only need 4 bits to represent up until the number 12. So yeah. So we compact it.
Yeah, this
Okay.
is why modulus 16. Now I got it. It takes the first part of the 8 bits.
Correct. I never gave much thought to it. Good observation. So this is our code so far. We have load immediate 10 into registry 7. Load immediate 5 into register 8. Add register 7 and 8. Write the result into register 1 in the accompanying bit mask. Next, we want to store it into the memory. I think you see the pattern here. Store is 59. So 59, store U8. Why U8? No reason. Could be anything you like. We store into the address VX W8 mod. Yeah. Okay. So tell me, WA, like which registry we should use for this instruction? You remember?
It's in the instructions, right? It's 7. No, it's you sum 7, 8. You use 7 and 8, and the result goes to 7, right?
1. It goes to 1.
Goes to 1.
Right. So we are interested in registry 1, and the address doesn't really matter. So registry 1 is of course the next bit, so we could just put 1. The address, whatever, a few bytes to specify whatever page or whatever position we want. So we will have 59, store 1 into the address. Into the address, yeah, this one. So this means the second page, blah, blah, blah. Some address.
Okay.
Now, I don't know if this is interesting. There's a little notes like housekeeping stuff. Because our program is 14 bytes long, we would actually need to pad the bit mask with extra 2 bytes because the bit mask is represented eventually as bytes, not as bits. So there will be this padding step. And then there's a little quirk, which I don't know for what reason, that the official test vectors and of course other teams are representing the bit mask by flipping the bytes. What I mean by that, let's look at our code so far. We have 100, 100, 10. Let's just focus on the first 8 bits. Right? Let's put it here.
So just one correction, maybe go back to the doc there, just for me to make sure
Yep.
I'm not wrong. So you put C equals, but this is not C, this is P, right? So our final program is
where our final program? You're correct. The P. This is the final program.
because C is a single instruction, P is the whole program, right?
Correct. You're right. The text here is not. Yeah. This is the entire thing. So what we have here, let's do two windows. Why it doesn't work? Happens.
And you can actually take this program and simulate in the PVM simulator,
Yep.
right?
Yep. That's the next step.
Got it.
PVM simulator.
Yeah.
Do we have such a thing?
Yes.
It's not a simulator. It's actually it's a real PVM written by other teams, and ours will be there soon. It's a debugger, not a simulator. Okay, so this is the final program. We have the length of the jump table, 0, because we don't use it. Then we have the encoding of how many bytes? Yeah, how many bytes we use to represent each element of the jump table. Well, it's just 1, right? We're not using it. Then length of C of our instructions, it's 14. Then the instructions themselves, because J is 0, it's empty binaries.
The P is the whole program and C is just the part of the instructions. No, okay.
Yes, yes. Then this is nothing. Then C is all of this, right? This is what we had. We had load, sum, store. And we're missing K. And this is a note about the bits mask. Although not specified in the GP, the accepted way to encode the bit mask is to reverse the bits. So we have this bit mask, which we've padded with 2 zeros to reach 16 bits in total, 2 bytes. We then reverse internally each byte. We reverse its bits and convert it into bytes again. So this is our entire program. Yeah, length of the program itself, and the last 2 bytes in our case is the bit.
Why do you have a 2? I see a 1 because up there you have the last. No, up there in the P you have 591001, right?
Yeah, I wrote this document hastily in like the last 2 hours, so you know.
And down below you have 1012 instead of 1001.
Can you point me where?
Yeah, so the final program after the 59. Here? After 59 you have 1001. And down there you have 1012 down.
Yeah, there should be a I'll show you in the
when you added the bit mask, you changed what you had before. This is what I wanted to say.
Yeah, what I meant to do was something like this, and K, and then talk about K.
Yeah, but down there, the final executable program.
Oh, this one.
No, down, go down.
Okay. Yes.
There.
Yes.
The end of the program is different. You have 591012.
Oh, this.
Yeah, it's different.
Okay. Yeah, I'll be honest. So when I write it in the PVM debugger,
yeah,
the last
just make
instruction.
Sure so it was just a typo. Just to make sure.
No, it's not. It's a typo, but there is a reason. When I run it in the PVM debugger, which you'll soon see, it's a fault in the store memory operation. I don't know why. It should work, but you know, this is hastily done. So that's why it's a leftover from me trying to move the page forward so it reaches an accessible memory range, which didn't work eventually.
Okay.
So there we have it, right? We have load immediate, How you like, hex or this? What's your preference?
How did you put the program there?
I did it like this.
Okay, you take the bytes and you create a binary. You can copy and paste also, if I'm not
It didn't
wrong.
work. It didn't work when I copy pasted.
Okay.
So I eventually went this route.
Okay, so you just copy the
I've
bytes,
written into file,
the bytes and load them into the PVM.
and then I load here.
Perfect, awesome.
Right, we have PVM test code. There it is. Now, full transparency, the store U8 operation doesn't work. I'm not entirely sure why. So we have load immediate, right? We've loaded, let's do decimal, easier for me. We loaded 10 into 7. We loaded 5 into 8. We sum both of them into 1, and this should work. It doesn't. Don't know why. So there we have it. That's a very simple.
Maybe you can try another PVM. There's another. You are using the typeberry version. If you choose another PVM, maybe it will
Yeah,
work.
I tried. It panicked. I guess I'm writing it wrong somehow. Not entirely sure what's wrong about it. No big deal. I mean, I'll find it out later.
Okay.
Wasim, how are you?
It's fine. Great explanations. It's clear for now.
Okay. So from here we can move on to the more advanced, so to say, calls. You want? Ready?
Okay.
Yeah, there's no reason to go every opcode, but let's see generally what it can do. Call through is just skip to the next one. Ecall is calls a host call. So this is the part that starts interacting with the Jamixer code or with the actual Gem client, with the work packages, with the work reports, like work packages for refine, work reports for accumulate. This is the part where this internal engine, throws like, okay, Gem client, do something. Load immediate. Okay, load something into a registry. Store things into memory. Jump, we know jump. Jump indirect uses a register value plus the immediate value. So you not specify the value directly, you offset from the register value.
Sorry, I didn't understand very well. What is the ecall instruction? What does it do? I see it everywhere, but I don't understand very well what it is.
Okay. Let's say you want to transfer balance between two accounts, right? How does that work? I mean, you have a PVM code, which is those binary streams, and in what point does a binary, which is completely in its own universe, goes back to the state and changes stuff? It can't. What it does, and we'll get to it, it calls a host call with a specific number. The number is an idea of what operation you can do. A new service, upgrade service, change gas, transfer, all sorts of stuff.
So this would be the IO. This will be similar to IO, like write to disk or something like that.
No, it's more than IO. This is passing the control back to the caller, like the caller, the gem that you, Daniel, knows. Passes a service code into the PVM. It runs, does all sorts of operations with the registry and the memory, internal memory. Yeah, and at some point it passes control back to you, the caller, with some instructions of what are you required to do. For example, transfer balance between two accounts. You do that. You put some evidence, so to speak, or outputs. Evidence is not the correct word. You put some outputs back into the registry or the memory and pass control back to the PVM. Now the PVM can operate on those. Like, you put something back on the registry or memory, and the PVM continues.
The same PVM?
The same PVM, the same one. Got myself with too many windows here.
Yeah, but there's an exit reason, right? It finishes the execution after the
What
equal.
finishes the execution?
Because there's an exit reason, H, and something
Oh,
like that.
exit reason. No, H is the exit reason that triggers the host call. We will get to it.
The host call.
Okay. There's no point running over the instructions. Like, let's just get to where you want to know about the host calls. There we go. Host call definition. An extended version of the PVM invocation, which is able to progress an inner host call state machine in the case of a host call hold condition is defined as this. So what's going on here? Man, I really hate those new yellow stuff that you cannot remove. I'm moving to a regular PDF. How's the font size?
Yeah, maybe a little bit bigger.
Still bigger?
For me, it's fine.
A little bit more. Yeah, perfect. Maybe you can hide the menu.
So this is the host call. This is the engine that passes control back and forth. So we start with let the exit reason, counter, gas, register, memory, all the things that you already know. Let it be the exit reason from the PVM, right? So we pass some binary, the PVM ran, and it exited with some exit reason. If the exit reason is halt, panic, out of gas, or page fault, like memory read write error with the address of the page fault, then nothing, terminate. You return where you are with the X. X is a context. We'll get to it. Don't fuss about it. If, however, the exit reason from the PVM is this one, which means host call, and you call the host call function and it exited with page fault. So the internal PVM exited with make a host call function. You made the host call function and it came back with a page fault. Then you return page fault and the current state. Now this is where it gets interesting. If the exit reason from the PVM is make a host call, you made a host call. The host call came back with new updated counter, new updated registry, new updated memory, and updated context, and continue. You call again to this function. You recurse with the new state from the host call. If the host call terminated either with a panic halt or out of gas, then that's the end of the execution, and you return with the latest state as updated by the host call. Now, I don't know if I can make it any reasonable without showing you code.
No, it's fine. You can show code.
All right.
But do you have like one example of what is one specific, what is the host call? What kinds of host call do we have?
Yep.
Just
Yep. Definitely have. So these are the host calls, right? Let's consider read. Read will read Daniel, you remember that services have storage, right? One of the key pairs, like key values mapping of a service account is storage, right?
Mhm.
The storage is a hash, actually not a key value map. Now, if the PVM wants to read a value from the storage, this is how it's done. It's calling the host call read, and this is identifies the service. It tries to read from storage. Then what happens here? Yeah, this is the read from storage. V is the service at the storage at the key. Something
So
FL.
can we compare the host call as something, let's say, similar to like operational system call, something like this, like read from the disk, read from memory, or read from network, or access other stuff that are not part of the CPU. So the PVM itself is just a CPU with registers and memory. But besides this, if you want to access some external stuff, you like the gem state, like what is in this, the data availability or the services storage. Basically, I would say mostly storage.
I guess you would. I don't know if you
host-
remember in a PBA there was a when we got the general explanation of how a substrate client is built, right? So you have the runtime, which is a WASM, right?
You're right.
Now the WASM doesn't know anything about the database, the storage, the networking, all those kind of stuff, right? Those run maybe different processes altogether, and it's definitely not accessible to the runtime. And it cannot be accessible to the runtime because that would be a major security risk, right? Especially in the case of Gem, where everybody can write their own service. You definitely don't want the service to just have, free for all access to whatever. So the way that the service can ask for information about like the Gem state is through the host calls. So in many ways, yeah, your analogy is
and basically you can only do host calls that you are authorized for. So you can't access data that is not part of your scope, let's say, put this way. Or you can read from anywhere.
I did not see any concept of authorization here. Like there's no, I don't remember any host call that checks.
I think in the refined logic there are some authorization stuff before.
But, you're right. But it's this is more outside. Like if we are in the inner core of the PVM and single instruction, now we move one shell outside. The authorization is another two shells outside. You're right. By the time that you get to the host call, that means that the service was already authorized to run as a whole.
Okay.
Yeah, Wasim, what you wanted to ask?
I wanted to ask, the set of host calls is already defined? I mean, in the paper, or?
Yeah, these are the set of host calls. We have three categories: general functions, which include gas, lookup, read from storage, write into a service storage, info about what exactly I don't remember. Okay, these are the general. So we have four of those.
Okay. It's like calling foreign functions, for example, between Elixir and Rust, for example, or C. We're calling a known function to the system remotely.
Yeah, they're indexed. This is the host call, the inner PVM host call will pass an index. And this is the index that triggers this or that operation. So we have in total 24.